All right, this is my third try on this problem. Twice I've recorded videos, edited them, and had them ready to post, but I'm just not happy with what turns out because this problem is easy. It's the kind of problem that on a test you can answer in 5 seconds. But trying to describe why it's so easy, counterintuitively, is kind of difficult. So what I'm going to do this time is I'm going to kind of lie to you a little bit and show you how you can get the answer. And then I'm going to go back and explain how I technically lied a little bit, but it doesn't change the answer. Hopefully this will be better than either of my first 2 attempts. So what's going on here is we're dealing with linear transformations. We got 2 of them, A and B. They both map R12 to R12. And what we know is that the dimension of the null space of A is 3, and the dimension of the null space of B is 5. And what we're interested in is the possible dimensions of the null space of the composition of these 2 functions. So first, here's the wrong way to do it that'll get you the right answer that isn't as wrong as this name suggests. As long as you understand what the null space is. In case you don't, this is just the set of vectors that get mapped to the 0 vector. The word kernel is also used for the exact same concept. An important fact about the null space, I don't know how much we use it in this problem, is that it forms a linear subspace. So the null space of some transformation T is a subspace of the domain that T maps to 0. So we can kind of think about this transformation B as taking these 12 dimensions and sort of partitioning them. 5 of them will go to the 0 vector, meaning the remaining 7 will not go to the 0 vector. That idea of partitioning the dimensions can be made a little bit more formal with this thing called the rank nullity theorem. And all that says is that the dimension of your domain, so 12 in this case, is equal to the rank, the dimension of the image, plus the nullity, the dimension of the null space. So in the case of B, I got 12 dimensions to play with. 7 of them go to the image because I'm told that 5 of them go to the null space. If you want, B is going to kill 5 of the 12 dimensions. Similarly, A has a null space of dimension 3. So what that means is when we apply A to R12, 3 of the dimensions get killed and the remaining 9 survive. They end up in the image. All this question is asking you is how many dimensions would get killed, would end up in the null space, if we applied B and then A. Well, let's see. B can kill 5 of the dimensions. A can kill 3 of the dimensions, so at most we can kill 8 of the dimensions. But wait a minute, what if the 3 dimensions that A kills were already killed by B, right? We don't know that A kills 3 of these 7 dimensions. We know that A kills 3 of these 12 dimensions. So if, loosely speaking, they kill the same dimensions, then I'd only end up with 5 dead dimensions. The answer to this question is D. That's really easy. I love this problem, but why'd you call it the wrong way? Well, technically what's going on here is I'm playing a little bit loose with the domain and codomain of these linear transformations. We're going to get the same answer, but if you want to really understand this problem, we're going to have to get a little bit more into the weeds than what we just did. It'll be the same idea, just cleaning some things up a little bit. So here's 3 copies of R12. I'm interested in the composition A of B, so I'm going to apply B first, and then I'm going to apply A. Because the dimension of the null space of B is 5, the dimension of the image of B is 7. That's this rank nullity theorem again. So if I apply B to all of R12 here, I'll be left with a 7-dimensional subspace of R12. This is the image of B. How did I compress this 12-dimensional space down to these 7 dimensions? Well, because I have this 0 vector, which is technically part of the image, which is why I kind of drew it on the edge here, that 5 of these dimensions went to. These 5 dimensions here that get sent to the 0 vector under this transformation B is the null space of B. So far, so good. Where I have to be a little bit careful is when I talk about A. I made it sound like maximizing the null space of this composition, in other words, getting as many of the 12 dimensions here sent to the 0 vector over here, was as easy as having the null space of A not intersect the null space of B. I made it sound like we could kind of toss our 3 dimensions of the null space of A out here in our picture and we'd be good. It's not quite that simple, but it is that idea. The reason that doesn't work is because the image of B is not all of the stuff outside of this purple circle. It's entirely possible that B maps elements from R12 into the null space of B. It's not sending them to the 0 vector. It's sending them to some vector to whom, if I applied B again, would get sent to the 0 vector. So it's not the intersection of the null space of A and the null space of B that I'm interested in. It's the intersection of the null space of A and the image of B that I'm interested in. If I throw the null space of A completely inside the image of B, remembering that the dimension of the null space of A is just 3, then all of these vectors would get mapped to the 0 vector, and the image of the composition would only be 4-dimensional. I started out with 12 dimensions, B killed 5 of them, which left me with 7, A killed 3 of those 7, which left me with 4. If the image of this composition is 4-dimensional, then the nullity of the composition is 8-dimensional, again because of our rank nullity theorem. 4 plus 8 equals 12. It might sound like I'm saying the same thing that I said before. B kills 5, A kills 3, 8 die in total. And that's true, you just have to be a little bit careful with this idea of killing different dimensions. The dimensions that A kills very well might be the exact same dimensions that B kills. Right? B might kill the first 5 dimensions, and A might kill the first 3 dimensions. That still might kill 8 dimensions in total if B maps the last 5 dimensions onto the first 5 dimensions. So because these dimensions can kind of move around under the transformation of B, you got to be a little bit careful saying things like A and B kill different dimensions, so they kill a total of 8. Really what you need to say is that the dimensions that A kills, the null space of A, lies within the image of B, the dimensions that exist after B does its killing. As you can see, that little subtlety is kind of hard to describe, which is why my first 2 attempts at this video were so bad. Hopefully this one clears things up a little bit. I've only pictured the case with the maximal nullity, so maybe I'll make the argument one more time for minimal nullity, in case people are still a little bit sketchy with this. I still need 3 beautiful copies of R12. I'm still going to first apply transformation B. Transformation B is still going to leave me with the 7-dimensional image, meaning 5 dimensions get mapped to this 0 vector. Those 5 dimensions are referred to as the null space of B. So far the pictures are identical. Now let's define transformation A. Really what I'm concerned with for transformation A is how much of this image is transformation A going to send to the 0 vector. If I want the nullity to be minimal, I want as little stuff sent to the 0 vector as possible. So I want to make sure that the null space of A lies completely outside of the image of B. I'm going to draw this 3-dimensional subspace a little bit carefully. Maybe I'll make it look like this. Sure. This is the null space of A, and it's 3-dimensional. Note that if I picture that null space over here, it's entirely possible that some of it lies within the null space of B and some of it lies outside of the null space of B. The fact that some of it lies outside of the null space of B might lead you to believe that more than 5 dimensions are going to live in the null space of the composition. But that's not true. We don't care about the intersection of these 2 null spaces. We care about the intersection of the null space of A and the image of B, because the only vectors that transformation A is going to get applied to are those that live in the image of B. So if the null space of A is completely outside of the image of B, then all of the vectors that A sends to the 0 vector are outside of the image of B. In other words, A doesn't send any of the image of B to the 0 vector, other than, of course, the 0 vector. So if the image of B were 7-dimensional, the image of A of B would also be 7-dimensional. Therefore, the nullity of the composition would only be 5-dimensional, even though this picture over here and the argument that I made at the start of the video might lead you to believe that it's more than 5-dimensional. Hopefully this picture illustrates that subtle difference. Again, like 5% of the video just to solve the problem and 95% to try to make clear this subtle difference.